There we go. Okay.
I'll just do that.
Okay, so that webcast is live. So
Okay. So they
you're
can
on
watch right
there. Yeah.
now. All right, so we're a couple minutes after 2:30, and I think the room's booked up right after this, so let's get started. Thank you all for coming. I'm really happy to introduce Dr. Bill Mills, who will be giving a talk on open science. So Bill is a research software engineer at Triumph. I think just been there
About a week.
About a week. And before that, he was working with the Mozilla Science Lab, helping researchers use open science tools. Okay, so he's an expert in open science, and I'm really glad that we can hear from him today. Welcome, Bill.
Thank you, Nancy. So as advertised, I'm Bill Mills, scientist and scientific software developer at these fine institutions most recently. Over the past year or so, I found myself doing a lot of study and thought on this open science movement. So who's heard of open science before? Anybody? Hands up. Anybody? Whole bunch of people. Excellent. We're winning the war. People have actually heard of this. That's awesome. So open science, when you first come to it, seems to consist of a ton of different ideas, different tools, different arguments, different things that people want to put under this very broad umbrella of the kind of wild party that is open science. And newcomers often feel kind of overwhelmed by all this variety. There's so many different things to do and learn, and it's not always clear how to inject that into your actual research that you do day to day. Despite all this sort of rich complexity that open science wants to dig into, it really boils down to a methodological movement that emphasizes these key values of transparency, reuse, reproducibility, and collaboration. And one of the first things I want everyone to notice about this list of values is that there is nothing new here, right? These ideas have been part of doing science in some form or another for as long as we've been doing science. What open science is really about is revitalizing these old priorities and these old ideas with new opportunities and new tools that are becoming available to us in the past 20 years or so. With the advent of the web, and it's really the web that sits at the center of the practical opportunities of open science, we have the chance to supercharge how we deliver on all of these priorities. And that fundamentally is what this movement is about. Okay, these are pretty big ideas, right? Reproducibility and transparency and all these things. But today I want to focus on things that aren't, big philosophical ideas, but rather things we can actually do, things we can dig into in our real practice as individual researchers and scientists And I also want to take the opportunity to present some of the evidence and arguments to suggest that these techniques actually deliver and actually work to serve not only our own careers, but our scientific establishment as a whole. So those core values that I started with map onto roughly 4 areas of action, in my opinion. So the first is open access, which is simply publishing your papers not behind a paywall. We should not have to pay an arm and a leg to get a hold of your research. Number 2 is open source, not only taking all that source code that you're writing to do your analyses for those papers and putting it up there, easy to access and free to access on the web, but also thinking when you're writing that software, how can I write this software in a way intended to be reused by myself and by my colleagues so we can stop reinventing software wheels over and over again and move forward as a discipline rather than as isolated individuals. Number 3 is open data. Ask ourselves, is there a way by getting more pairs of eyes on the data that we collect to derive more results, ask more questions of that data so that we can get as much out of it as possible, and to buttress the reproducibility of our research by letting people actually dig into our raw data and confirm our results in a way that we have an unprecedented opportunity to do today, now that we can effectively distribute our data like never before. And number 4 is maintaining an open communication model designed to assemble collaborations around all these other elements of open science, which really at its heart is what open science is all about, bringing people together to collaborate on their work rather than working in isolation. Okay, so we're going to dig into these for the rest of today. So number 1 is open access. One of my favorite particle physics papers ever. It was not about the Higgs. It wasn't about dark matter or anything like that. It was actually a paper about publishing. Physicists have been putting their papers on the archive. For anyone not familiar with the archive, this is a preprint server that will host free copies of preprints of papers on the web, and you can access those anytime you like. Physicists have been putting preprints of their papers up on the archive for as long as the archive has existed, so over 20 years now. That's enough history that a few of my colleagues realized that, hey, we could actually do some statistics to this data set. We could actually measure how open access publishing has affected physics and the physics establishment. So they did so. And the first interesting plot that came out of their work was this. So what they did was they took a few decades of high energy physics papers and they split them into 3 cohorts. Cohort number 1 was only published in traditional closed access journals, so behind paywalls. Cohort number 2 was only put up on the archive, not submitted to a traditional journal. Cohort number 3 was submitted both places. And after a while, once people sort of caught on to what the archive was and became familiar with it, the impact factors of the cohorts of articles published only in a journal or only on the archive became indistinguishable from each other. What's more, the cohort of articles who were published in both places garnered 5 times as many citations as their cousins published only in one or the other place. This is a tremendous data-driven insight into the impact of open access publishing. It showed us that not only can open access dramatically increase the citations and the circulation that our research receives, but it's more nuanced than that, right? It's not enough to just slap it up on the internet for free. This traditional system of peer review to ensure the quality of our paper still matters and still an important element in our publishing paradigm. We must combine both to be on that very highly cited top curve up there. My colleagues continued digging into this and tried to study how this effect evolves over time. So what they did is they took 2 of the biggest high energy physics journals, took all the papers from them, and split them up into either also submitted to the archive or not submitted to the archive. And then they plotted the average number of citations per article per month for those cohorts. And what they found, and I apologize for the teeny tiny scale out there, is that those articles submitted to the archive got significantly more citations for 10 years after the publication of those articles in their traditional journals. So this has a long-lasting effect on how much our papers circulate and what impact they have on the scientific discussion. In addition to the longevity of this phenomenon, they also noticed that about 20% of the lifetime citations of these articles came before they were ever released in a traditional journal. So that big vertical line there is T0 for publication in a traditional journal. And so they dug even deeper into this and said, okay, not only is it really important to make our papers available open access after, or perhaps before even, having them peer reviewed in a traditional paradigm, immediacy of communication has a tremendous impact on how much citations we get for our work and how much it affects the scientific conversation, which is sort of makes sense when you think about it, right? Because of course, people are going to be excited to talk about what's happening right now, what's hot off the presses in your field, as opposed to things that are now as much as 2 years out of date in the traditional publishing paradigm. So immediacy also has a huge impact on the volume of our conversations. There's a whole other dimension to this open access argument as well. Earlier this year, when the Greek government defaulted on their debts, academics and students and labs and universities across that country immediately lost access to all those closed access journals, terribly hindering research, of course, in that country until they could resolve their political problems and challenges. You don't have to wait for a budget default. At many institutions and places around the world, every single budget cycle, many places have to decide which journals will we keep and which can we no longer afford to give access to our students and researchers to. When people lose access to these journals, that hinders your research as well because it slows down the scientific conversation. We could be making progress on the ideas that we want to be talking about in our literature, but we end up dragging our feet because of obstacles like this. And if it seems far away, if it seems like something you've never had to deal with, even Harvard, one of the wealthiest academic institutions in the world, has for years been struggling to pay for all its journal subscriptions. Struggling so much that Harvard's administration has put pressure on academics, faculty at Harvard, to only publish in open access journals. Think of how aggressive that is. Trying to tell your faculty where they should and shouldn't publish. Harvard wouldn't do that if it wasn't serious, if it wasn't a problem that needs addressing. So because of the tremendous citation advantages we can get from open access publishing and the great need to relieve ourselves of these financial burdens that journal subscriptions are costing us, people in high energy physics are starting to win the war in open access publishing. So in this plot from the original paper I was talking about, they took 5 of the biggest high energy physics journals and plotted what fraction of those submissions made it into the archive by early last decade. It was basically all of them. So what I would like to see going forward from this is to go the final lap and make this not an ad hoc practice that we kind of do when we feel like it, but a matter of policy. It's something that we do across fields of research. So other people are picking up this refrain as well. Our colleagues down in the States have something called the FASTER Act, enjoying bipartisan support currently in front of their Senate, an act which mandates that any research organization receiving at least $100 million in federal funding in the US must publish its papers open access by 6 months after the publication of those papers in a traditional journal. So many of us are going to either work for or work with these major scientific producers. Legislation like this will affect us, so we need to get ready as early as possible to understand how to fold open access into our workflows. So my to-do number 1 for everybody for this talk is, please, for your next paper, get a preprint of it on the archive, or a different preprint server if there's one more appropriate for your field. Students and postdocs, I am especially talking to you. I don't want to be a huge bummer, but the scientific job market is not awesome right now. It's really tough to get jobs. You need those citations on your CV if you want to compete for those faculty jobs, for those postdocs, for those academic positions. Don't leave that factor of 5 just sitting on the table when we can have it pretty much for free. Okay, the second pillar of open science is near and dear to my heart as a scientific software developer. It's open source. So open source got its start in the 60s with early ARPANET request for comments conversations, when the thing that would eventually become the internet was getting its start, on through hobbyists exchanging basic scripts on bulletin board systems in the 80s, on to produce some of the most substantial and impactful software we have ever had. As scientists, we invest a huge amount of time and effort into developing software, developing bespoke software for our own analyses and our own usage. I'd like to take some time to think about how these folks were able to cobble together these diffuse teams of like-minded individuals to produce, like I said, some of the most impactful software we have ever had. So to talk about these open source collaborations, it's instructive to look into a little bit what makes a good open source contributor. There's been a ton of research on this in recent years. Zoulimakis, linked at the bottom here, found that there were 3 ingredients to a good open source contributor. I insist on tacking on respect at the bottom of that list, because if you act like a jerk to your collaborators, it's not going to work. But anyway, back to Zoulimakis. They pointed out that a good open source contributor must, of course, have the ability to contribute to relevant tasks on the project. They must have the opportunity to do so, and it's best if they see themselves as a potential user of this project. Now, I submit that the first 2, ability and opportunity, are actually trivially satisfied in the sciences. Of course, we come up with projects that surround our interests and skills, so we can work on them. And this is our full-time jobs, so we have the opportunity to work on them. The really interesting one is the importance of contributors on these projects being potentially users of this software. Because when you think about that and sort of turn that around, you realize that open source communities are really little incubators of software reuse. Expert programmers, expert software developers don't, when they want Python or when they want Linux, they don't go sit in their little silo in their lab on their laptop and try to program it themselves, all by themselves. That's madness. And you will never, ever, ever be able to achieve the heights that those organizations and teams did by working together. An effective open source collaboration knows that they need to share and reuse code amongst themselves if they want to produce something of that quality. And that is how those diffuse, under-resourced teams have punched far above their weight for decades now in the products that they're producing. So some colleagues of mine over in the UK at the Software Sustainability Institute did a big survey a couple of years ago, examining how much people are using software and bespoke software in their research. And maybe completely unsurprisingly, everybody uses software in their research. If so many people are using software, and even software they create themselves, in their research, there must be opportunities for us to find chances to collaborate and reuse each other's code so that we can move forward as a discipline rather than reinventing wheels individually over and over and over again. There's a game I like to play at conferences and hackathons with scientists that when I go there is I'll get maybe a few people around a table and I'll get them all to shout out what they're working on right now, like tweet length description of their current project. Invariably, there will be a pair of people that are doing almost exactly the same thing and could share code on that project and could learn from each other. How many people do I need to play that game successfully? Seems to be about 8. That's how common overlap is in researchers working on code for their research. Another aspect of sharing code rather than keeping it locked up privately on our laptops is that people ask me all the time, they come to me and they say, Bill, I'm a new graduate student or I'm a postdoc or whatever, I have to write a lot of software for my research. How do I get better at programming? Should I take a class? Should I buy a book? No, don't waste your time. The #1 way to get better at programming is to get feedback on the code that you're producing. Put it up there where people can see it and ask for feedback from your colleagues, from more experienced programmers, because they can lead you to the ideas that are going to help you write better code in the future. Why am I so fixated on you all writing better code? It's not because I want you all to be professional programmers. It's because your time is worth more than endlessly coding things and reinventing software wheels. I want you out there doing the science that you actually want to be doing, not wasting time struggling with software that shouldn't have to be that tough. So that is the way to improve those skills. So, okay, that's great. There's all kinds of different opportunities that open source software presents to us. We could improve our skills as programmers. We could stop reinventing software wheels. Or we can increase our efficiency by reusing each other's software, making higher quality projects. There's just one problem. Who knows what I'm working on right now? Anybody? Nobody. as scientists, it's really hard to find out if another scientist is producing code that would be useful for you to use in your own project, even if that code is being distributed open source. Google does not index these things very well. Trying to search for that, it's totally futile, right? That never ever works. So as long as it remains difficult for us to find out if there's other software projects that we would like to reuse and collaborate with, an open source community will never take off in the sciences. So we need to find a way to overcome this discoverability problem. So if you think about it for a second, we can imagine a solution that's already sort of half on the table from what I've already said. So I'm imagining this future where we can easily discover each other's software projects and reuse them. And if we have a good experience with that software, we're going to tell our friends. We're going to say, hey, I solved all these problems with this software that I inherited, and I didn't have to spend all this time writing code myself. Isn't that great? How can we operationalize that word of mouth? How can we make that part of our standard practice? That's kind of a trick question. You all already know the answer. You all already do it all the time in a different context. Any guesses? Anything? Second big thing I want to see people start doing is publishing and citing the software that they're using. So if we start citing our software in our papers, which we're going to put on the archive as well, then we create the opportunity for scientists to ask the question, who's writing, or who's doing research similar to my own? Who's doing science related to mine? And each and every one of you know exactly how to answer that question. Right? That's a question you always have to answer whenever producing any piece of research. You have to have that background literature all reviewed. If that background literature also cited the open source software that it was using, it would be a trivial matter for you to say, oh, I'm just going to grab that software off of GitHub or off of wherever they're sharing it from. And we wouldn't have to play this awful game of like, what's the right search keyword? Or who can tell me about some project that I'd like to use. We can bake it right into our literature in a way that's kind of costs us nothing, right? It's just adding 1 or 2 references to the bottom of your already existing citation list. So in order to facilitate this process, GitHub is offering yet another service to help you do this. Just before I move on, who's heard of GitHub? Who's like, they've seen GitHub before? Okay, so if anyone hasn't encountered GitHub before, it's a website that provides a bunch of free tools for helping you collaborate and share code that you're working on with your collaborators. So one of the services that it offers in partnership with Zenodo as of a few years ago is that they will stamp your code with a DOI, a digital object identifier, which, if you haven't seen that before, is a serial number that corresponds to a permanently archived copy of your code, so that you can use that serial number to make that citation that I'm talking about. As they conveniently provide you here, it takes about 10 minutes to work through this the first time, more like 2 minutes after you've done it once. It's pointing and clicking at some stuff on their website. It's not very hard. And it will let us create that virtuous circle of software discovery, reuse, and citation, engendering more. So my to-do number 2 for everyone, please, for goodness sakes, for that next paper that you're going to put on the archive, also take the code that you use to do that analysis, put it on GitHub, stamp it with a DOI, and cite that code in that paper. Okay, we're at the halfway point. We've gone through 2 of my pillars of open science. Let's take a quick look back on what we've had so far. Open access dramatically increased the amount of citations we were getting for our work. Open source not only increased the efficiency with which we produce code for our analyses, but also helped us become better coders. Any good scientist knows that once you find a good thing, you just keep playing that game over and over again, right? What wonders await us if we start releasing our data openly and availably on the web along with that code and those papers? So to answer that question, there's been all kinds of research done. One of my personal favorite papers was done by a couple colleagues of mine right here in Vancouver. And one thing they looked into was, hey, well, does open data lead to more citations of our papers? And they found, yeah, releasing data in the collection of several thousand genomics papers that they used as their data set resulted in about 10% more citations than their colleagues who didn't release their data got. So a little citation bump, certainly not the 500% we got from open access. But the much more interesting part of open data is what it does for the amount of results we can squeeze out of a given data set. So I apologize for the super skinny line on this plot that makes it really hard to read, but I promise what it says is that as people in genomics released more open data sets, the amount of papers using those data sets also tracked similarly upwards. So people are actually using that data that gets released. Okay, good start, but that's not really good enough, right? There's still a problem with that logic. Who is reusing that data? Because if it was the originators of that data set, then publishing open data didn't matter, right? Because they could have still published those papers without releasing their data. So we have to ask ourselves who exactly is doing this reuse. And Heather and TJ did exactly that. And they dug into another graph meant to be looked at on a computer and not a projector, and found that it was in fact third parties reusing this data after about 2 years of that data being available. For the first 2 years, it was mostly the original authors publishing all their ideas that they had while they were collecting this data. But afterwards, third-party reuse of this data increased to a level where it ended up lifetime representing about half of the citations of that data set came from third parties. So turn that around, and naively, we're getting about a factor of 2 in papers and results out of data sets published openly, which is maybe not too surprising, right? Because fresh eyes have new ideas. People in your field that do something related but not exactly the same might be able to ask interesting questions of your data set that you either didn't think of or you just didn't have time to pursue because you've got other stuff that's sort of more relevant to your personal interests. So we got a small citation benefit out of publishing our data openly, but really what we're going to get out of open data is tremendously more bang for our buck in terms of the amount of results we can squeeze out of every single data set. This is crucial because for most of us, the majority of our money and the majority of our time goes into collecting those data sets. That's the really expensive part of doing science a whole lot of the time. We cannot afford to leave results on the table. I mean, who's got lots of money for their research? Nobody, right? We need to make those resources as productive as possible because we aren't getting budget increases anytime soon. So we need to get as much out of it as we possibly can. And open data seems to demonstrably contribute to this in a significant way. So over in ocean and atmospheric science, NOAA down in the States is not only providing services to redistribute open data in ocean and atmospheric science, they're also offering services to help you archive your data. So you can submit data to them, and they will archive it for you and redistribute it for you as part of their open data service. And if you dig into their website, they say that this service is designed to help meet requirements for data documentation sharing and archiving, operative word being requirements. More and more funders, more and more journals are making the release of open data a requirement for funding or for publication. So this is something we are going to have to deal with more and more as time progresses to meet those obligations. So it's not just NOAA that's jumping on the open data bandwagon. My old colleagues at CERN, at the Large Hadron Collider, also opened an open data portal recently where you can download open data from the LHC experiments. And if you dig into their website, I actually really love the writing on this website because it's very diplomatic, it's very polite, it's all very politic. But if you read between the lines, CERN calls out a few concerns with open data, and they're concerns that I share, particularly as we're putting so much pressure and so much money and effort into this open data infrastructure. There's some things we need to think about first to make sure we get as much out of open data as possible. The first concern that CERN had about making open data work is when exactly should we release this data? Because of course, you, as I said earlier, spent all kinds of money and all kinds of time to collect this data. You don't want to just give it away before you've had a chance to publish on it. Of course you deserve first crack at publishing on the data sets that you collected. No one is going to argue with that. So it makes sense to have a reasonable embargo period on data sets before we release them openly. In genomics, thanks to Heather and TJ's work, it looks like 2 years, 3 years, because that seems to be about when all the first-party publications on that data have tapered off. Maybe data sets take longer to analyze in particle physics. Maybe they need 5 years. This is a conversation to have within your fields and decide what a reasonable embargo period for your data is. The Second element of making open data work is one that I have been very, very vocal about lately. And I call it ensuring data legibility. If we take our data, we slap it up on the internet, and nobody can make heads or tails of it, this has been a complete waste of time, right? That's completely useless. We want people to actually consume that data, to actually use it to produce new results, not just to warehouse it and forget about it on the web somewhere. That's pointless, right? That's not what we want. We need to go to lengths to make sure that our colleagues can actually consume this data effectively. And so what CMS, one of the experiments at the Large Hadron Collider, did was they made a whole virtual machine to contain their data and also have like an analysis framework that ships along with that virtual machine, so that you can easily spool up the analysis framework inside that VM and analyze that data and be able to understand and do analyses on it, which is fantastic, and huge kudos to my colleagues at CMS that they did that. It's a tremendous amount of effort and a tremendous commitment to data legibility, but I think we can do even better. I think we can do better by thinking about how we can make our data legible without having to build this huge complicated virtual machine and ship like analysis software along with our data. That's way more work than anyone really has time for in most cases. We need something easier. And not only easier, I think we can find a way to make our data legible that doesn't just serve our own experiment, which is what we do when we ship some complicated infrastructure to go with it, but serves our entire field. And the way to do that is to think about standards for our data. How can we agree a standardized format for our data that everyone in our field can understand? Because if we can do that, then all of a sudden my data looks exactly like your data. And so it's really easy for us to swap data and analyze each other's work because it looks exactly the same. It's all in the same format. One example of this working brilliantly came out of geography. A while ago, they agreed this GeoJSON standard that was a standard way of encoding geographical information. And after agreeing that standard, a whole bunch of people started producing GeoJSON data, and a whole bunch of other people started producing like tools and apps and stuff that consume GeoJSON, and they all just fit together. They didn't have to work together. They didn't have to have endless arguments about like, why doesn't your tool understand my data? Why doesn't your data fit in my data? No. It all just worked together because they agreed a well-articulated standard and they all stuck to it. This is called interoperability, and it's a key element of reusable engineering. So we don't have to relearn how to read data every single time we get some new data. Once we have a agreed upon data standard in our field, then we can also release a parser for that data format relatively easily, which is something that will read that data format on disk and spit it out into something in memory that you can do your analysis on. And I don't care what language you're into or how you want to do that. Could be a NumPy array if you like Python. Could be data frames if you like R. Could be a C class if you're a C person. Whatever, right? Whatever your field thinks is useful and thinks is interesting. Once we write that, we are of course going to share it open source. And then the exercise of using open data no longer has this long, tedious data munging period before it. We can just ingest the data and start doing the science that we actually want to spend our time doing. So for a real live working example of one of these data parsers, I recently published to 1.0 just like last night, a Python parser for the World Ocean Database data format. Anyone uses that. So it's available at this link at iQuad/WADPy on GitHub. Check it out. It will ingest raw World Ocean Database data into either NumPy arrays or Pandas data frames, whichever you prefer to work with in Python. So my to-do number 3, part A, is discuss a standard data format with your colleagues in your field if you don't have one already. And to-do number 3, part B, is get that data out there in that standard format and release a parser to help read that data as well so that we can consign to history struggles with data munging and be able to easily read each other's data. Now, if you're looking at that and saying, oh my goodness, I cannot get my entire field to agree on a standard. Yeah, it's true. That's really hard. That's going to take a long time to get people to sign off on a universal standard for data. If you can't get your field to do it, focus on just your lab group. What if just the people in your lab could easily share data and read each other's data and use it in their analyses? That in itself alone is a huge step forward for a lot of labs that wouldn't have to struggle to read each other's data anymore. And if you're thinking, oh man, my PI will never agree to that, I'm never going to be able to get my lab on board, fine, do it for yourself. If you could record your data in a standard format really, really strictly and be able to easily consume it with the same parser that you write once and once only, you will get that problem if out of the way, if not for your whole field, then at least for yourself. Release that data in that format, release that parser to consume that data. And I think you might just find a couple years from now, a few people who are not really into your data standard that you came up with saying, well, there's all this data out there that I can have for free, and there's a parser that will let me read it. Maybe I'll play ball with this. And after a while, you may just find yourself responsible for a de facto data standard that does permeate your field. Sometimes it just takes one person to start that activity. So the fourth and final pillar of open science that I want to talk about and introduce today is open communications. So if you think about everything we've talked about so far, you could think of open science as a communication protocol. How do we communicate about our data? How do we communicate about our code, about our papers? On the theme of communication, it behooves us to think about how communication can serve that last key value of open science. Anyone remember what it was? My 4 key values of open science? The last one was, yeah, that's a good one, but that was another list. Collaboration. Collaboration was a key element. It's really the engine that drives productivity and results in open science. So to think about, so earlier we talked about what makes a good individual collaborator. It also behooves us to think a little bit about what makes a good collaboration at scale. We do not have time to dig into that in the couple minutes that I have left for this talk. But one key element of it is understanding where advocates of these projects come from. A successful collaboration needs to have champions. People that go out and say, this data set is awesome. This piece of software is fantastic and we can solve our problem that we've been having without having to reinvent the wheel all over again. Having those champions go out and tell people, tell their labs, tell their colleagues about their research is how these collaborative projects take off. And I submit that a simple pathway to advocacy looks a little bit like this. Once someone becomes aware of a project that might be relevant to them, they start participating a little bit because of course it's open source up on GitHub, right? So they add a few features, correct a few bugs, whatever. And as time goes on and they use it more, maybe they make more substantial contributions. And then one day they wake up and they feel like that project is their baby too. They now have a sense of ownership of that project because of all the effort they put into it. And then you have them. That is when they are going to do what I started out by saying, and go back to their labs, go back to their research groups, and really advocate for these projects and attract new collaborators to them. That's a pathway for building these champions of our collaborations, and it's a key element of building successful collaborations. One element of this that is so crucial to point out in context with communication is that this is much more effective in early stages of a collaboration. If you're level 1 awareness, when there's already 200,000 lines of code in the project, oh man, that sounds like a lot of work to try and read through all that and understand how to participate in that. It's much easier to follow this pathway if you get on board with a project early on in its development, so that it's easy to understand where the project is at when you first come on board with it, and so that your ideas have a chance to really impact the evolution and growth of this project. All the decisions haven't already been made long before you ever got there. Being able to have impactful contributions to a project really kickstarts that sense of ownership, moving forward to being an advocate and helping build these collaborations. But we need to talk about these projects as early in their infancy as possible to generate these power collaborators, if I may. The challenge, and I finally get to communication, and why communication matters for this, is that scientific communication is incredibly formal. Traditionally, we have 2 channels of communication. We can publish a paper, or we can give a talk at a conference. In either case of these communications, a whole bunch of our colleagues will have reviewed that content first, made sure it was as exactingly perfect as it could possibly be, and pushed it to the limits of technical sophistication. Because of course, we don't want to publish mistakes in our conference proceedings and in our journals. And of course, those limits of sophistication is where discovery happens. That all makes sense. And nobody's contesting that or saying we shouldn't do that. We absolutely do need that highly refined and sophisticated communication model for all the purposes we've been using it for so far. But when you restrict topics and communication to a very highly manicured set of things and ways of doing, you send the message that there isn't a lot of room for other ideas, for new thoughts and new things that might be a little bit half-baked, or maybe sort of, need a lot more work to think about. No one wants to get up at a conference and talk about something that is just sort of not really developed at all yet. They want to participate in that really formal and sophisticated communication model. We need secondary channels that let us have those low-stakes communications, that let us bring up kind of wild and crazy new ideas that are just starting out without it feeling risky, without it feeling like we're jeopardizing our reputations as scientists. So how are we going to do it? Where are we going to get these casual communication channels from? Well, there's a million different ways to do it. I will just go through 4 possible tools that can really help us with this. My personal favorite is a simple GitHub issue tracker. Because you're putting all your code on GitHub now, you'll also get an issue tracker set up for free automatically with each and every one of those repositories. So for those that haven't used the issue tracker before, it's a message board, like any other message board on the web. You can use that to start conversations about your projects to fold in those new contributors, like I was talking about early on in your projects. And if you would like some guidance in more depth on really effective use of the issue tracker, see the Working Open Guide from my colleagues at the Mozilla Science Lab. This is like a workbook describing techniques for creating effective collaborations on GitHub and on the web, and it specifically emphasizes effective use of the issue tracker. So lots of rich detail and information there. So click on that link to check that out. Another thing that I'm a huge fan of is blogging, simple old blogging. Blogging is a fantastic channel for scientific communication because it's so flexible, right? You put anything you want in your blog, and no one's going to take it, too seriously. Really, it gives us that mouthpiece to start having those conversations, to ask those questions and put those ideas out there in a format convenient for us. There's a million different blogging platforms out there. I won't go through them. If maintaining one of those blogs still sounds like too much work and you just don't want to do that, have a look at something called the Journal of Brief Ideas. This is a project from a colleague of mine, Arfin Smith, and others at GitHub also. And it's Arfin's tongue-in-cheek joke with himself to call this a journal. It is not a journal by any stretch of the imagination. What the Journal of Brief Ideas is it's a website that will publish articles on anything in science. The only rule is the article is at most 200 words long. I think a lot of scientific publishing could benefit from this model. But that way, and they also provide comments so people can ask questions and comment on your articles. They even stamp it with a DOI, so you can cite it later if you really want to cite your brief idea. That way you don't even have to maintain a blog, right? You can just put up a brief idea and get people to comment on it like that. Another thing really popular in the life sciences, particularly right now, is services that pre-register studies before they're conducted. So some fields are really struggling with something called publication bias right now. This is rampant in fields where publication favors positive results. So drug trials that actually worked and produced, an effect on a positive effect on their study group. Is that if you don't publish your failed results that didn't produce a positive result, then other teams might have the same idea you had and waste all kinds of time and money repeating work that didn't need to be done because they didn't know that it had been done before, because we don't publish those things. So this pre-registration service is designed to defeat that by saying, okay, I'm going to do this study, and then you can look up and see whether it worked or not, whether they have a full paper published behind it or not. The fourth and final tool for effective low-stakes communication in the sciences is, in fact, Twitter. Now, I admit, I took a long time to warm up to Twitter. It just wasn't my thing for a really long time. But I realized that it's actually an incredibly effective tool for distributing and aggregating links to these other conversations. It's really hard to stay on top of everybody's issue tracker. It's really hard to stay on top of everybody's blog, right? You're not going to be clicking refresh on those every single day that you come to work. That's silly, right? No one's going to do that. Twitter used well can be a really effective communication tool in the sciences by distributing links to more substantial conversations, like your issue trackers or your blog posts or whatever, so that when you want to start a new conversation about an idea, when you want to invite new people to participate, you can easily push those links and those calls to action out on Twitter, and people who will be interested in that will follow you, and you get those delivered to them in a nicely structured way. So it doesn't involve actually going out and finding these things. What does that mean? It turns it into a pull rather than a push, or a push rather than a pull, depending on your perspective. Okay, whatever. It makes it easy to collect links about these things. So my fourth and final to-do for getting involved in open science: blog early, blog often, discuss your projects that you're working on, see if there's people that would like to work with you on them, and carry these collaborations forward to do more and better than we ever could working in our little silos on our own. Okay, there's much more nuance to all the topics that I've talked about today. There are far more and more radical things involved in the open science movement that I haven't even discussed at all today. But these have been the basics, the 4 fundamental tasks that I think will be a tremendous leap forward for the sciences if we can all participate in them. So to review, the 4 things that I would love to see scientists do across the board: get your next paper, a preprint of it, up on the archive. For that paper, publish the code on GitHub along with it, and get a DOI on that code and cite it in that paper. Think of a standard format for your data that as many people as possible can use, and release that data along with your paper. And always, always, always talk as much as you can about the projects that you're working on to try and create these collaborations, and find people as early as possible in the research cycle. There's so much more that we could be doing, that we should be doing, but these things, if everyone could just do these, that would be a massive power up for sciences across the board. So the reason I put so much energy and so much effort into advocating open science and doing this research and talking about these ideas is that I believe that this generation of scientists has the chance to do more and reach further than any generation of researchers that have come before us, because of the cultural forces that are afoot, because of the tools available to us now, if and only if we can find a way to effectively collaborate with each other better than ever before. That's what open science is all about. Thank you, everyone. This has been a practical introduction to open science.
So we have some time for questions, so please feel